Single leader replication has one fundamental limitation: all writes must go through the leader. That means the leader is both a performance bottleneck and a single point of failure for write availability. For many systems, this is fine. A single leader in a well-chosen data center can handle write loads that most applications never approach. But two specific scenarios make single leader replication genuinely painful. The first is multi-data center operation. Imagine you have data centers in the US, Europe, and Asia. With single leader replication, the leader is in, say, the US. Every write from a European or Asian user travels across the Atlantic or Pacific to reach the leader, gets written, replicated back, and the response travels back. That's 200 to 400 milliseconds of added latency on every write latency that users notice. The second scenario is clients with offline operation. Consider a calendar application on your phone. When you add an appointment while offline, that change is stored locally. When you go back online, it needs to synchronize with the server and with your other devices. Each device is essentially acting as its own leader while offline, making writes independently. Every device is its own replica. CouchDB was specifically designed for this model, supporting peer-to-peer replication between devices. The book also notes collaborative editing, Google Docs, Figma, where multiple users simultaneously edit the same document. Each user's browser is effectively a leader, accepting local writes instantly, while their changes propagate to other users. Multi-leader replication adds a leader in each data center, or treats each client device as a leader. Writes go to the nearest leader, replicate to the others asynchronously. Write latency drops dramatically. Write availability survives single data center failures. But multi-leader introduces a problem that single leader neatly avoids: write conflicts. When two leaders accept writes to the same data at the same time, what happens? In a single leader system, write conflicts are impossible by construction. Two clients might try to write the same record simultaneously, but the leader serializes them. One write goes first, the other sees the updated value and either succeeds or fails with a conflict error. The application can retry. The result is deterministic. In a multi-leader system, two leaders can accept conflicting writes simultaneously with no coordination between them. Leader A in the US accepts a write setting a meeting title to budget review. Leader B in Europe accepts a write setting the same meeting title to Q3 planning. Both writes succeed locally. When the two leaders synchronize, they have different values for the same field in the same record. Now what? The simplest approach is conflict avoidance. If all writes for a particular user, or a particular record, always go to the same leader, that leader serializes them and conflicts never arise. A user editing their own profile always routes to the data center nearest them. As long as they don't move data centers mid-session, no conflicts occur. The book notes this as the recommended approach when it's feasible, and the techniques for implementing it are essentially the same as sticky routing for read your writes consistency. But conflict avoidance breaks when a user travels across regions, or when a data center fails and traffic is rerouted. At that point, you need a strategy for conflicting writes that have already happened. The options converge toward consistent state. All replicas must eventually hold the same value, but they reach it in different ways. Last write wins. Assign each write a timestamp, discard all but the most recent. Give each write a unique ID, keep the higher numbered write. Merge the values somehow. If two users both edited a document, produce a merged version. Record the conflict and present it to the user for manual resolution, what CVS, Git, and similar tools do. Each of these has a cost. Last write wins loses data, whichever write was timestamped earlier is gone. Custom merging logic is complex to write correctly. Manual resolution puts burden on users. There is no free option. The book is blunt about one of the most common conflict resolution strategies. Last write wins, or LWW, achieves the goal of eventual convergence, but at the cost of durability. If two writes occur concurrently, LWW will drop one of them silently. The client whose write was discarded received a success response, but their data is gone. Last write wins requires every write to carry a timestamp. But as we'll see in Chapter 8, clocks in distributed systems are not reliable. Two machines can have clocks that differ by hundreds of milliseconds. A write that happened later on one machine might carry a lower timestamp than a write that happened earlier on another machine. LWW will pick the wrong winner. Cassandra uses LWW as its default conflict resolution strategy, and Cassandra's documentation explicitly warns that it can lose data. A more principled approach is CRDTs, conflict-free replicated data types. CRDTs are data structures specifically designed so that concurrent modifications can always be merged in a deterministic, order-independent way. A counter CRDT can be incremented by multiple nodes simultaneously and the results always merge correctly. A set CRDT can have elements added by multiple nodes and the union is always correct. RIAC supports CRDTs natively as a way to avoid conflict resolution entirely for certain data types. For more general data-rich documents, arbitrary key-value structures, the application must define its own merge logic. The most robust approach is to preserve both conflicting values and surface them to the user or application for resolution. Git does exactly this when it marks merge conflicts in your code. It refuses to choose and makes the human decide. Version vectors, which we'll cover in depth with leaderless replication, track which writes caused which other writes. They let the system detect which values are genuinely concurrent versus which is causally more recent. With version vectors, you can detect conflicts precisely instead of relying on timestamps. The fundamental lesson: in a multi-leader system, conflict resolution is not a feature you can add later. It must be designed up front, before any conflicting writes occur, because the resolution strategy determines what data is preserved and what is lost.